Okay. Hello, everyone. I'm Sajjad, your TA in this course, one of your TAs. And I'm also doing my PhD right now at U of D, and my specialization is in databases. And specifically, I'm working on vector databases right now. Before that, I was working on some succinct, very CPU efficient indexes for some novel hardware. Just to double check, can you see my screen and also hear my voice? Perfect, thank you. Also, feel free to share your video. It just makes everything easier for me to interact with you. And this is a completely new topic, so I think, I need to know if some part for you guys is too fast or too slow, so I can adjust myself. And yeah, I think that's it. We can start. Is there any question before that? I'm also recording, by the way. Okay. So, um, did anybody hear about vector database before? Or is this the first time you're hearing about it? I see. Um, okay, sounds good. So that means there are lots of things to learn. So for vector database, it's basically a database. Instead of attributes, you're storing vectors. So instead of imagine you have a database consisting of names, IDs, family relations, I don't know, like incomes, anything like that. Instead of that, or additional to that, you're also storing some vectors that represent that primary key or that object. So, for example, you can imagine that you have an image, and that image has a bunch of information embedded inside itself. But obviously, we cannot store all of that information because it's just too much information. So, but you want to have a sense about the general overview of the image, what it is generally about, and what it does represent. So you convert that image to a vector, to an embedding of the image, and in a way you try to recognize the patterns in the image and just store that specific vector inside the database. So if you're storing vector in a database, it's a vector database, basically. As I said, we are here in vector databases, we are storing embeddings. It's useful for pattern recognition. In a way, it's just the semantic of the media. It could be text, it could be image, it could be video, it could be sound, anything. And it's usually highly multidimensional, because if you want to store the gist of the image, you really need to, store that information in multiple dimensions, because in only one dimension you cannot really say anything about that image. And yeah, so if you can imagine that you have 100 million of these vectors stored in a database. So the question is, if you want to query these vectors, in a way, if you are interested, if you have an image and you are interested to find relatively close, relatively similar images to the image that you are interested in, how do you want to do that? So again, let's go back to relational database management systems. They usually create indexes like B trees, or I don't know, hash tables to speed up the search. But here, because we don't have an intrinsic sortable attribute in our vector, it's not easy at all to create a B tree. So again, in B-tree, we have only one-dimensional data, and we just simply sort that, and based on that comparison between two attributes, we can place it in the B-tree and traverse the path. But in vector database, it's hard to create something similar to B-tree. Does it make sense at all, what I'm saying? Okay. If there are any questions, let me know and just interrupt me, please. Okay, so if you look at the picture on the right side, a query comes in. This query is, for example, for this specific image, you want to extract similar images to that query. You can imagine the query is mapping to the red point, and the other points are the points that already exist in the database, in the vector database, and you just simply extract similar images and return it to the user. The nice thing about vector database right now is that it's heavily used in large language models, in LLMs. So one problem, there are many downsides with LLMs. One of them is it's hard to update LLMs, keep them updated. It's very hard. So people solve that with different approaches, but the main approach right now is to keep the most recent news, most recent events in a vector database. And whenever your LLM is being asked by the user about something very recent, on the side, also query the vector database. And as the context, give that to the LLM. So your LLM is now, in a way, it's not trained by the most recent events happening right now, but because you have a vector database, you can retrieve that from your vector database and give it to your LLM. So again, look at the picture. Here, a query comes in, and you have an embedding model. It could be like the embedding model that Cohere, for example, or ChatGPT is using. And with that embedding model, you map the query to a vector, basically, to an embedding, to a vector. And then you issue a vector query search to your vector database and retrieve the nearest neighbors, in a way, the closest related images or documents, and then pass it as the context to the LLM to answer your query. And then your LLM is able to answer it with much higher accuracy. It's also useful in terms of privacy because sometimes people want to store their own, like, I don't know, you can imagine in banking industry, you want to store your customers' information in a highly private manner. And in that case, you don't want to share your data with OpenAI, probably, right? So in those cases, you also want to use OpenAI, but at the same time, you don't want to give OpenAI all of your data. So you store all of your data in a vector database, basically the embedding of your data in a vector database. And whenever you want OpenAI to give you a better answer, just attach the relevant document, the relevant vectors to the context. And then your LLM is able to do that without compromising your privacy. So this whole process, people name it as RAG, Retrieval Augmented Generation. Basically, it generates document embeddings at first. Then to query that, we generate embedding of user query, get relevant documents, create a prompt, which is which is given that specific context, and use LLM to generate the response. Does it make sense? Oh, sorry, I don't know why I don't see questions in the chat. It's yeah. So Gary asked me, so there is no key really. So like any other vector database, you are storing ID or primary key in a way for each object you are storing here. The main attribute in your database is the vector, but like any other database, you still need to identify that specific object, that specific vector. So you are still storing some ID for each vector. That ID could be implicit, like it could be just based on the position you are storing your vector in the disk. Like the first vector you are storing, the ID would be 0. The second vector, the ID would be 1. You really don't need to store that ID, but people usually also store a UUID, a universally unique ID for their objects. Any other questions? Okay, let's speed up then. So again, just quickly give you a motivation to learn about vector database. It's very useful right now in AI. It's core to LLM. I don't know if you guys use Cursor or not. Cursor is basically a fork of VS Code, which is highly yeah, it's using AI beside your day-to-day development as developers, and the basis of that is basically a vector database. It gives you opportunity for a smarter search, as I told you, in people who are interested in systems, in database management systems. Right now, the most relevant research in between AI and system is in vector database. I'm not saying it's a good thing necessarily, but vector database right now is a very hot topic. Also, if you know about vector database, it's probably going to be very nice for your career. It's easy to work with. It's very easy to work with. There are a bunch of open source and lightweight vector databases out there. You can just simply use them. And I know many companies that use vector database, like very small companies, not necessarily be obviously like Netflix or Spotify, they use vector database every day, but for all of your queries. But like very small companies, a simple search in their database, they could use a vector database to give you better results. And there are a bunch of cool projects out there, which is a nice thing. So if you are also interested in open source contributions, there are nice projects in GitHub that you can contribute to. So the difference between let's talk about the difference between RDBMS, Relational Database Management System, and Vector Database Management System. So the most important thing that I want you to understand from this table is that vector database really probably deserves another kind of database. There are many people that argue otherwise, but I don't know. We need to wait for another 10 years to find out if vector database management system is completely a different thing or not. But let's just see the difference here. So in a traditional database, we are storing records. In a vector database, we are usually storing vectors. And the vectors are the first, like the most important citizens in our database. Type of queries we are executing in a traditional database is relational algebra, but in vector database, it's not that complicated. It's just simply nearest neighbors and sometimes simple filtering and hybrid search. Again, in traditional databases, we're doing join, group by, using foreign keys, but none of those really matter that much in vector database. It's relatively easier to do updates, inserts, deletions in traditional database. It's not easy at all to do that for a vector database, and usually you update the whole vector, like you change the whole vector, so you need to change a bunch of things. And as we will see later, it will also basically destroy your index over time, which is not the case, for example, in B-tree. If you change some record in your B-tree, you just need to update your B-tree, which is possible in log time. Also, in traditional database, consistency is more important. People do a bunch of things for handling transactions. It's not, again, it's not the case in vector database. People only care about eventual consistency. And yeah, so in terms of storage, so this table is probably wrong. In terms of storage, actually, vector database also use LSM trees, which is very interesting. You know about LSM trees, I assume, right? I think you do. Okay. So yeah, actually, vector database also use LSM tree, and I don't know any vector database that don't use LSM tree. It's yeah, as their object storage, they all use LSM tree and basically build the index of the vector for each SS table. We will see how we can build indexes for vector database, but yeah, actually in terms of storage, they're very similar. In terms of hardware, we want to use heterogeneous hardware in vector database because there are a bunch of tasks that are highly parallelizable, especially during index building. So if you have some GPUs laying around, you can use them and optimize your index building time. And also, in terms of architecture, vector databases are more disaggregated. This is, I think, partially because vector databases are a new topic relatively. So people approach this problem in a, I don't know, in a more professional manner in terms of software engineering. In the old days, like 1970, 1960, it made sense to create things monolithically because you didn't have that many CPU power. You just need, and development was also very hard. Network was the bottleneck. So microservice didn't make sense that much sense that time. But now people are migrating to microservices or like Lambda functions or this kind of things. But still, changing the old architecture is very hard. So still now, most of the traditional databases are implemented monolithically. That being said, there are many sophisticated and very well-known people in database world that believe vector database is basically it will be added to normal databases in future. Right now, it's very hot, and people think, "Oh wow, this is something that we need to build something very specific to handle fast queries." But it's not going to be the case. At least they say that. Like, I don't know if you know Andy Pavlo or not. He has a very nice course. He is a professor at CMU. He has a very nice advanced database system course and also introduction to database systems. I highly encourage you to take a look at it. Let me also write his name in the chat. Yeah. So this happened before, like the first time NoSQL was introduced, people were very interested and they said, okay, SQL is dead. Relational database system is dead. And but we now see that actually Postgres now support that, and people now simply use Postgres to do that. It's like people thought MongoDB is the next big thing, but right now we see that didn't happen. Also, like we had a hype for graph databases. Again, um, it gets digested into the SQL world. So this could be the case for vector database too. And there is this loop that, I don't know, we should wait to see what happens. So the key challenges in a vector database is, first of all, it consists of large and dense vectors, which makes it hard to navigate and find the nearest neighbors, to do fast and accurate queries. Also, there is no natural structure, as I said, and there is no natural structure between two vectors. Like you can't say one vector is bigger than the other. That doesn't mean anything. Like the vector, each attribute of the vector is comparable to the attributes of another vector, but all these attributes combined, like all of these dimensions combined, you cannot say one vector is bigger than the other. And the criteria of the search is actually a bit vague. There is this gap in vector database world that people in theory actually measure the accuracy of a search differently than the people in using in practice. It's very weird, but like if you read theory paper, they have a different definition for recall than people from practical perspective. But yeah, so if we want to measure the closeness, the similarity of two vector, you need to define a similarity function, or basically a distance function. So people usually use one of these three things: Euclidean distance, which we all know, inner product, and cosine similarity. So to give you a better intuition about it, Euclidean distance is, as you know, you can see the difference. I think I don't need to explain that. The inner product is the projection of one vector to the other, and just multiply the size of these two things to each other. And the cosine similarity is basically the cosine between the two vectors. And if you are interested in finding the similarity between two vectors, one simple thing that you can do is to just compute the distance between two vectors, either by using Euclidean distance or like cosine similarity, or also inner product. You can somehow measure the similarity of two vectors. And then based on that, you can say, okay, this vector is a very good candidate for me to return to the user because it's very, very close to the queried vector. Okay. The problem is that the exact k-nearest neighbor is very slow. So you can imagine that you have, like in real world database system, you have 1 billion vectors stored in your vector database. And if you really care about the nearest neighbors, the exact 10 nearest neighbor, we need to go through all of those 1 billion vectors and compute the distance, which is very, very hard to each distance computation, if you are working on a highly multidimensional vector, is also a hard task to do. Like it's not very fast. There are a bunch of floating point operations. You can speed up these operations by using SIMD or GPU, but again, this is like a very energy intensive, very slow task. So brute force approach is usually not a good choice. People sometimes use that for small data sets, like until 100K vectors. But beyond that, you probably need to, go with a heuristic approach. And get back the approximate k nearest neighbor, because that is much faster. So again, approximate nearest neighbor is a solution. It returns the k likely neighbors. It's not always exact, but it has a very, very good accuracy usually. Like, to give you an intuition, it's something around, people in industry, depending on the use case, use something around 95% accuracy. So it's good. And it's a bit, it's less accurate. It consumes more memory than the brute force approach, because you need to build the index, and the index itself sometimes is huge. And the updates is also harder. Like, in a completely flat search, in a completely brute force search, if you want to add a vector, you just add it to the end of your vectors, and then during the search you just need to go further to search that specific vector. But if you're creating an index to check the approximate nearest neighbor, then it's not trivial to update the index. So for approximate nearest neighbor, you always need an index, basically. Is there any question until now? Okay. So let me give you an indexing example for now. So let's assume that we have this black dot as our vectors, and we want to create an index. One approach would be to just cluster these vectors into different partitions. And whenever a query comes in, like this blue ball here, you go to the cluster that its centroid is the closest to the queried point, and just check the vectors that belongs to that specific cluster. So in this case, this blue dot belongs to this cluster, the green cluster, because it's the green cluster centroid is the closest to this blue dot. And then we go and check all of these vectors that we know probably are good candidates to be the nearest neighbors, and just return the top, I don't know, in this case, top 3. The problem with this approach is we may miss some neighbors near the boundaries that belong to other partitions, like this vector. But this is just an example for indexing. So there are different index types for approximate nearest neighbors. The first index is just simply a flat index. It basically stores vectors directly in a table. There is no structure. It is able to give you the exact answer and with brute force, but it's slow. It's very slow to search. The other index is locality sensitive hashing, or LSH. It's a very, very interesting approach. I will talk about it later. But basically, the intuition is we hash similar vectors into the same buckets. So you can imagine that if you have two images that are very, very similar to each other, and you give these two images, the embedding of these two images to the LSH, the LSH returns you a bucket in the hash table that is same for both of these images. In a way, we are trying to increase the collision for highly similar embeddings in an LSH. The next approach is a tree-based index, which is basically a hierarchically hierarchically partitioned space. And some example for that is RP3 and NOI. Actually, I think you guys learned about KD3 in the course, right? So KD3 is one of the things that people used at some point as a vector index. We will talk about it later. Also, there are cluster-based indexes. Usually, the people combine some compression approach with the cluster-based index because by storing the clusters, you're basically doing some compression over your vectors. You are compressing your vectors to the centroids it belongs to. And the last approach, which is the most effective approach until now, it may change next year, I don't know, is a graph-based approach. So you basically create a graph, connect your vectors in a smart way together, and then search the graph to find the k-nearest neighbors. So let's just go through each one of those and learn about them more concretely. And please also interrupt me if you have any question. Let me check the chat. Okay. So again, flat index, you are just storing vectors contiguous to each other, or I don't know, in any manner you want. You don't store any index. You basically, during queries, you just go through all of those vectors and compute the distance, and then return the closest ones to the user. It is highly parallelizable. It has a very fast GPU implementation. But again, GPU is very expensive, and probably people are more interested to use GPU in their training, in their, like, I don't know, LLM training or other AI training tasks, rather than using them in their vector database. People usually want to use, I don't know, CPU in a vector in a database. Yeah, the overall scheme is very simple and easy to understand. The second approach, as I said, is LSH. So for now, let's compare LSH with a normal hash function. So in a normal hash function, different items, even slightly different items, are mapped to different hash locations. Even if you have very similar but not identical items, that's the case. So for example, in the picture on the left side, if you can see, the picture, like the first vector and the second vector are very similar to each other. But they are being mapped to two different positions in the hash function, in the hash table. And the most important characteristic of a normal hash function is minimizing collisions, which is not the case in LSH. So in LSH, hash depends actually on the location, and closer items are mapped to the same hash position in the hash table. And in a way, we are maximizing the collision for similar items. So again, for V1 and V2, we see that they are being mapped to the same location in our hash table. Is there any question about LSH? Also, theoretically, it's relatively concrete approach. People come up with a bunch of theoretical bounds, upper bound, lower bounds for LSH. But in practice, it's not fast, and the accuracy is also low. So measuring the similarity in the context of LSH, I assume you're asking, in the context of LSH, one simple hash function you can imagine is you can partition your space by some random subplanes, and basically whenever two vectors are in the same side of the partition, you assign them to the same location in your hash table. So very simple approach. Like in one-dimensional let's assume you have a one-dimensional vector. In a one-dimensional vector, you can imagine a LSH that checks if the value of your key is less than 0 or bigger than 0. If it's less than 0, it gives you 0. If it's bigger than 0, it gives you 1. So like if you have -1 and -3, which are, I don't know, close to each other, it gives you back 0 for both of those. But like if somebody is asking you the similarity between -10 and 10, they are being mapped to two different parts of the partition. So they're mapped to 0 and 1 respectively. Did I answer your question, Gary? Sure, perfect. So isn't this essentially the same thing at the center? Very good observation. So I would say LSH, the people in LSH world, they come up with more theoretically concrete approaches than the people from cluster-based world. So in cluster-based, you can go crazy. You can do a bunch of things and like fit into the distribution of your data, fit into the distribution of your query, and come up with better clustering approaches. But that's not the case in LSH. In LSH, it's a highly investigated area, like from 1970, 1960s, but like it's a very old topic. And in those approaches, people usually are very careful about the functions they use for the LSH. And to be honest, it's not being used in vector databases right now. At least I don't know any vector database that use LSH in a daily basis. Maybe they combine LSH with something else. Again, I'm not aware of those vector databases. But yeah. But you're right. That's a very good observation. Like in a way, any compression technique, again, centroid is a compression technique. Any compression technique that you can imagine is under the hood is basically an LSH, because you are mapping a bunch of vectors that are similar to each other to an index of a hash table, and it's obviously lossy compression. Any other question? Okay, very good questions. So let's move on. The next approach is tree-based indexes. So I think you know about KD trees, right? Can you verify that, or that you heard about KD trees, K-dimensional trees? Okay, so I think I will go through that and make sure you guys remember that. Again, as far as I know, tree-based indexes are useful in vector databases, but again, they're not the best practices. They are not state of the art. But yeah, KD3 is one of them. Annoy is a paper from 2020, relatively new. It's a variation of a specific kind of tree, RP tree, and it basically recursively splits the data set randomly. It's an interesting approach, but again, it's not a very fast approach. And there are tree-based indexes, but for the lack of time, we won't explore them that much. But yeah, to give you an intuition, what is a KD tree? Let's assume we have two dimensional vectors, and we want to index these vectors using KD tree. So at first, we find the medoid, or the medoid line of the first dimension. So partition based on the medoid, based on the median in one of the dimensions, and add the node to the tree corresponding to that line. So right now, line 1 is basically the line that separates the upper side and the lower side of our space. And the next level is basically, again, we just recursively do that, but now for the other dimension, for the vertical dimension. And we come up with two different lines again, line 2 and line 3, which again, you can see, for example, in line 2 is separating the top subspace into two partitions. The right partition has 4 vectors. Also, the left partition has 4 vectors. So, you know, it's relatively a easy approach to understand. And you just continue to do it recursively. Like again, line 4, 5, 6, 7. For each one of the subpartitions, it again creates 2 new partitions, but for the next dimension, which is again the horizontal dimension. And you just recursively do that until you partition all of your vectors into their specific location, to their specific subpartition. And the query is basically, if you're interested in like a vector that resides in partition, if you're interested in a vector like vector h, you just go through 1, 2, 5, 11, and after 11, you know which partition is for h. So this is KD3. Is there any question about KD3? Okay, so people usually don't use tree-based indexes in practice, but I see more interest in tree-based indexes, at least in practice, than LSH indexes. But I don't know, like it could be this field is very, very trendy and new, and like low-hanging fruits are usually in graph-based indexes and clustering-based indexes, which I didn't talk about yet. I will in a few minutes. But the thing is that because there are a bunch of low-hanging fruits, people don't pay enough attention to these nice, theoretically concrete methods, because it's harder for people to understand and harder for people to like reason about. And I think there is high potential in both tree-based indexes and LSH indexes, but yeah, we should wait and see. So the next one is cluster-based indexes. Again, remember the example I gave you before? It's basically you select the number of clusters you want to create in your search space. So for example, in a two-dimensional world, you can cluster into three different partitions. And whenever a query comes in, you select the centroid that is closest to that query, and then just traverse all of the vectors that belong to that specific partition. The problem with that is you may miss some nearby vectors, especially very close to the borders, and you may miss some neighbors in other clusters. So to resolve that, actually, let me ask you, how would you resolve this problem? Does anybody have any idea? Very good. Yeah, people actually do that. Yeah. So one idea could be like you can have overlapping partitions, and there are some problems with that, but like especially in updates and deletes. But yeah, actually people do that. So in a way, you increase your search space. But do you think it's what is the effect on query time if you create overlapping partitions? Do you think the query time would be better off or worse? Also, feel free to turn the microphone on. Yeah, it will be worse because again, you are searching a bigger subspace. So in a way, it's a trade-off here. But can we actually, I don't know, somehow improve things without uh, harming the query performance? Can you think of any idea? So again, to state the question again, the question is in cluster-based indexes, if you are only looking at one cluster, uh, if you're only looking at the closest cluster, you may miss some vectors that are very close to the queried vector, but are not being considered because they belong to another cluster. So the question is, how can we resolve this? One approach that Dimitri said is to use overlapping partitions, which is a very good approach. One other approach that people use is also considering, instead of only considering the nearest partition, nearest cluster, we can consider top three nearest clusters. So in this case, you will consider all of these three clusters and go through all of these three clusters. But again, like overlapping partition, this will increase the query time. And let me ask you this. Do you think if you increase the number of dimensions, right now in this example, you only have 2 dimensions, but if you increase the number of dimensions to, I don't know, like 128, which is a realistic dimension, do you think this problem becomes worse? Like it's harder to solve this problem or easier to solve this problem? Very good. Yeah, actually, I don't know if people do that or not. Um, but one approach that you can definitely do is to just simply store the vectors ordered by their distance to the centroid of that partition. And whenever you're observing that some of your nearest neighbors or belong to the like latter part of the partition, latter part of the vectors, latter part of the subspace, then you probably know you need to be careful. So you can adapt yourself in a way. Like instead of going, like if you are super close to the centroid, you don't really need to consider other partitions. But if you are not, you're probably, at least you know you need to consider other partitions. That's very nice. Good job. But yeah, going back to my question, do you think this problem becomes worse, like harder to solve or easier to solve if you increase the number of dimensions? Yeah, yeah. And can anybody reason about it? It would be harder. Can anybody reason about this problem theoretically? Like how much harder? Is it linearly harder or is it exponentially harder? I don't know. Um, does anybody have any idea? So just give me your intuition. What is your intuition? Do you think it's linearly harder or exponentially harder? Yeah, it's actually exponentially harder. So for example, in the case of moving from two-dimensional to not two, but like to be easier. Yeah, it scales with each dimension. Exactly. So you can imagine going from one dimension to the two dimensions. In one-dimensional vector database, which doesn't exist, basically it's a simple database, you have at most one closed partition you need to go and check. But in two dimensions, if you're looking for other partitions, if you look at the things very close to the corners of the partitions, you need to traverse maybe three other partitions. This also happens in three-dimensional data. In three-dimensional data, actually, you need at most seven other partitions you need to traverse. So it's actually 2 to the power of dimensions minus 1. But this is like the worst case that could happen for you. But yeah, so all of these cluster-based index suffer from this problem. There are some, some ways that we can improve them, but it's usually like still it's a hard problem to solve. Okay. So yeah, as I said, one option for us is to, instead of only looking at one cluster, let's look at four close-by clusters. But as we said, in high-dimensional, multi-dimensional data, it basically doesn't solve the problem, because if you really want to solve the problem, you need to tune M to be exponential relative to D, the number of dimensions. And like it will just explode your latency. So let's now look at graph-based indexes. So this is the state of the art. So this is very important for you to understand if you want to understand anything about vector databases. Basically, the idea behind the graph-based index is to just create a vector. Create a graph over all of your vectors. And your graph should be very smart because, let's assume you create a fully connected graph. And whenever you're doing a search, let's assume you are starting from the root of the graph. I don't know, like from one node in the graph. Basically, if you are connecting to all other nodes, you need to check all other nodes. So it regress to brute force search. So you don't want to connect your nodes to too many nodes. But at the same time, if you connect your nodes to too few nodes, then you cannot do effective search in your graph. So it's a hard problem to solve. Also, it's important to find the best candidates for each node to connect that node to them. So one approach could be connecting each node to its closest neighbors. I don't know, we can talk about it if it's a good idea or bad idea. But also the other approach could be connecting to like further away nodes. And I don't know, like this could also have its own benefits and drawbacks. But generally speaking, graph-based indexes, at least in practice, there is no theoretical proof for that. Graph-based indexes that are being used in practice, they give you log n search time. So it's very good. Like in cluster-based indexes, in practice, they usually give you square root of n search time. But in graph-based indexes, they give you log n search time. And again, I cannot state it, it's very important to you to understand that all of these log n and square root of n, all of them are computed in practice. They are not ground truth. They are not theoretical, because we cannot reason about them theoretically very concretely. So yeah, so basically there is a type of graph. The name is RNG, relative neighbor graph. At first, I think it was introduced in 1980. It's a very important graph, but it found its way to vector database world around 2012, I think. And from that point, it's changed vector indexes until now. We don't go too deep about RNG, but it has some nice theoretical guarantees. Basically, all of the vector indexes that are graph-based, they try to heuristically construct um, a, a more sparser version of RNG and give you a nice graph with high accuracy. So there are different kinds of graph-based indexes. The most famous ones are HNSW, NSG, and Vemana. And yeah, so let's talk about HNSW for now. So HNSW stands for Hierarchical Navigable Small World. Um, it it's basically yeah, it basically consists of different layers, and each layer only each layer has exponentially smaller number of nodes. So the top layer has in this case has only 2 nodes. The layer number 1 only has 4 nodes. Layer number 0 has 8 nodes. So top layers are exponentially smaller than and the layer on the bottom. And um, it is basically constructed based on combining two different data structure that was highly well known at the time. The first one is navigable small world, and the other one is skip list. So let me first talk about navigable small world. Navigable small world is actually, again, a heuristic for RNG, relative neighbor graph. So it's hard to explain navigable small world, to be honest with you, but the idea is that for each node, you want to be able to reach to its nearby vectors with very few number of hops over the graph, right? Because what if the thing that you're querying for is like the node uh, you're standing on right now. So you need to connect most of the edges of each node to its nearby vectors. But at the same time, you want to connect the edges, some edges to farther away vectors, because you want to traverse your graph very efficiently. So let's assume you start from the root node of your graph. You go through the paths to find to find the closest ones to your query. If you have very small edges in this path, this causes you to like go through O(n) number of edges, at least, to get to the nearest neighbors of your query. But if you have few long and connected to further away edges, then you can skip bunch of small paths and just jump to the area that is very close to the query. So for example, in this picture, if the entry point is this blue dot, you just quickly jump to the other blue dot, which is a relatively a long jump, and you don't traverse the other smaller nodes. And then from the second node, you jump to another node, and then from the third node, you jump to the other. As you can see, over time, the size of each edge you are traversing is becoming smaller and smaller. Again, this is something that people observe in practice. It's not theoretical, but this is the intuition behind NSW. You want to connect some nodes. You want to connect your node to some nodes that are relatively further away, but also you want to connect them to their closest neighbors. So this is the overall intuition. Is there any question about the intuition that I just gave you? Is this clear? Is it clear why we are connecting edge nodes to their closest neighbors and also to some farther away neighbors? Okay. 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 Um, yeah, I didn't talk about complexities yet. I think you mean about the complexities in this slide. So let's, um, yeah, to be honest, all of those are basically non-theoretical complexities, so it doesn't really mean that much. But the most important thing in this slide about complexity is this line. The problem is that the average out degree to create some graph to like preserve a search path of O log n, the number of hops to be O log n, and the average out degree should be O log n. And you know, in highly scaled vector database, O log n could be a big number. And like also, this is the average out degree. You could have the case for some nodes that you are connecting that node to like 1,000 or 10,000 other edges. And basically, it increases your tail latency hugely. And this is very bad for your database. People really care about tail latency in database systems. So it's not perfect. We need to, fix some problems with it. But the idea is, again, to remain in log scale, log n time in the search path, but at the same time preserve, at the same time connect each node to not that many nodes in the graph. Okay. About the complexities, I think, yeah, to be honest, I don't have a better intuition for you uh, to give you, but if it's still very unclear, let's discuss. But specifically, other than the complexities, if there is anything else that doesn't make sense, uh, let me know and ask me. Okay. So this is navigable small world, but again, HNSW has a hierarchical architecture. So the other thing in HNSW, the hierarchy is basically very similar to a skip list. Do you know about skip list? Okay, let me go back and explain it. So one approach to capture the neighbors is, let's assume you want to connect each node to four closest to four other nodes. You can choose the two closest nodes to each node and just connect each node to its two closest nodes. And then for the rest of the edges, which are two edges for each node, you just connect these two edges to random part of the graph. So at the end, each node will end up with four edges. Two of those edges are connected to the closest nodes to that edge. The two other edges is basically just random connections in the graph. So the first two helps you navigate the graph if you are very close to the target, if you are very close to the query point. The second two, those two that are connected to random part of the graph, helps you to navigate the graph much faster. Does it make sense? Okay. Thank you for asking. So the hierarchy in the HNSW is basically very similar to a skip list. Do you guys know about the skip list, or is it the first time that anybody mentioned a skip list in this course? Okay, so a skip list is basically uh, con consisting of multiple layers. The bottom layer is basically a sorted list. That's it. Sorted list consisting of all of your all of the values that you want to store in your database. Right now, I'm not talking about multi-dimensional data. Skip list is something for one-dimensional data, simple float or integer. Okay, so the bottom layer is basically a sorted list. One layer on top of that, you just toss a coin and flip a coin, and if the coin, I don't know, with some probability, if it's like higher than 50%, you add each node to the top layer. So for example, and you just continue doing that until the root of your skip list. So for example, here we have 3 layers of a skip list. The bottom layer is again a sorted list, simply a sorted list. Layer number 1, we basically flip the coin and decide the promotion of each node that we in each entry that we inserted in the bottom layer to the top layer, and just we recursively do that again and again until we end up with two entries in the top layer. Does it make sense? Okay. So the idea of it, the hierarchy in HNSW is basically a similar thing. So at the most bottommost layer, you want to store the whole graph, which is very, very dense, which is slow to traverse. But in each upper layer, you want to store exponentially less number of, fewer number of vectors. So for example, layer number 1, we are storing, I don't know, 7 nodes here. And in layer 2, we are only storing 4 nodes. And at first, our entry point is in layer 2, in the topmost layer. We go through the layer number 2. And whenever we cannot get closer to the query points in layer 2, we just move from layer 2 to layer 1. And do that recursively in layer 1 again. Find the closest node in layer 1 to the query. And again, if we cannot get closer in layer 1, we move to layer 0. You could have more than 3 layers, and you just do this exact same algorithm. There is a small detail here, though. The small detail is that whenever you are jumping to layer 0, again, the same problem in clustering could happen. It's not a clustering problem, but you don't necessarily want to jump to only one node from layer 1 to layer 0. To maintain higher accuracy, you jump to 3 or 4 or like another number of closest nodes from layer 1 to layer 0. So for example, in this picture, from layer 1 to layer 0, we jumped to 3 nodes, and we traverse layer 0 from 3 starting points and return the top nearest neighbors. So does it make sense? HNSW, does HNSW make sense? Okay. So yeah, the nice thing about HNSW is the out degree is bounded by construction, and you don't have those annoying nodes that are connected to, I don't know, 10,000 other nodes. And this is very nice. This is very good. Also it's hierarchical. So again, skip list time complexity is log n, NSW is log n. So the total time complexity would be still remaining log n word. We actually observe that in practice. And it's nice. Like if you have a log n search time, it's usually something that people are okay with. Yeah. Yeah, there are a bunch of parameters that you can tune. I think we don't really need to go too deep in those things, but one parameter is EF search. EF search is basically the number of nodes that you want to traverse from layer 1 to layer 0. For example, in this case, EF search is 3. Yeah. And that's it. Yeah. So to give you an overall overview of all of the indexes we learned today, the flat index is exact. It's consuming very small amount of memory. It's gives you the opportunity for fast updates. There is no rebuild necessary when you are updating things, but it's very bad with at highly scaled data sets, highly large data sets, and it's not feasible for them. IVF, which is basically cluster approach, sorry for the name mismatch, is decent in the speed, has good accuracy, but it's not the fastest. Also, the rebuild is a problem in clustering approach because you can imagine one cluster gets exploded by too many inserts, and like the clusters become too big. So you need to somehow handle that big cluster. One approach could be dividing the cluster into 2 other clusters, but this could end up in a very bad and weird cluster shapes. And at the end of the day, you harm your accuracy. So there are a bunch of papers about that vector indexes are not very good at handling updates without complete reconstruction of the index. So in practice, the thing that people right now are doing is that they handle some incremental update, but like every day or every week, they rebuild the index from scratch. And it seems like a dumb approach, but that's the way people are handling this problem. HNSW has excellent speed, excellent accuracy, but it needs rebuilds again. And also the memory consumption of HNSW is even worse than clustering because of multi-layers you have. And usually the edge list size is also big. So like 64, 32 edges you are connecting to. This is not the case for IVF or like cluster-based indexes. And you just have more parameters. And if you have more parameters, it gives you the opportunity to optimize the index more accurately for your query and data distribution. But it's harder for people to like tune these parameters. So the ideal world would be to only have like one parameter or no parameter, and that your data structure tuned with everything by itself. But something like B-tree, for example, is a good example. Like B-tree is optimized for disk sector size or like the page size. You don't really need to tune B-tree that much. We just plug it in and use it. LSH has bounded errors. It has fast updates. No rebuild is necessary, but it's not feasible for large vectors. It also consumes high memory because the LSH function is usually it's complex function to come up with. And it's also rarely used in practice. Tree-based indexes, they are good for low-dimensional data. I mean, like less than 10 dimensions. They're deterministic and interpretable, but poor in scaling and slow updates, and also rebuild are necessary. So that was about indexes. Do you guys have any questions about it? Okay. So, yeah. So just give me 2 minutes. I need to use the restroom. I will come back very soon. Okay. So I guess you can hear me now. Let's continue. Perfect. So, we talked about different indexes, but also there was this mention of compression in my talk. So one approach for compression, because again, let me give you the motivation. Vectors are usually very, very huge. Like, yeah, if you have embeddings of OpenAI, I think it's more than 10, more than I don't know, definitely more than thousands of floating points, and like it's getting larger and larger when you are going to um, incorporate more accurate vectors for embeddings. So it's very memory inefficient to store this whole thing. So in a way, we want to quantize each vector or in other words, we want to compress these vectors to still represent the same information, relatively the same information, but in fewer bits. Obviously, we lose a bit of accuracy. We will see that it's not the end of the world. And actually, with some techniques, we can remain in a very high accuracy world, like something around 95%, 90%, but reduce the memory to 4% of the original memory. So exponentially, we are consuming exponentially less memory, but only losing few percentage points of our accuracy. So it's nice. It's nice for some applications. There are several main approaches, but the three most important ones are scalar quantization, vector quantization, and product quantization. We will go through each one of those, and at the end of this topic, we will end our class. So scalar quantization is basically, it's a very simple approach. We try to find the minimum and maximum of each floating point in our vector, and we try to just keep the first of all, we reduce, like we deduct the minimum of each vector by, like, we reduce the minimum of each vector from its from all of the attributes in our vector. And we also have another attribute, the name is bin size. So we basically map each 32-bit to 8-bit. So you can assume that your search space is getting smaller 4 times. So it's nice, X4 less memory. And also the comparison would be faster. And it's highly useful in, highly used in industry. And it only costs you 1% recall loss based on Qdirect, which is a company in vector database work. So it's commonly used in vector databases. Again, this is like a very simple technique. It's widely used in other domains too, like just computing. Like if you have 10 numbers and these 10 numbers are again like 1000, 1001 until 1009, one simple approach to losslessly actually compress these 10 numbers is to just reduce 1000 from all of these numbers. So you will end up with 0, 1, 2, 3 until 9. And you just need to store 1000 once. And you know that the other points are, whenever you want to compute them, you just need to add 1000 to all of the other points. So this part of scalar quantization is lossless. The part that is lossy is actually mapping each 32 bits to 8 bits. Because you need to come up with some bin size. So you can imagine that still you want more compression, and you want to map each one of your attributes into 2 bins. So if, for example, in the case of 1000 to 1009, you end up with, if you want to store your vectors into 2 bins, probably the number 5 is a good differentiating point for your vector. So again, in this example, you will end up with 0 to 9. Anything that is smaller than 5, you want to represent it by 0. And anything that is bigger than 5, you want to represent it by 1. So at first, you needed 4 bits to store each one of these numbers, 0 until 0, 1, 2, 3, and until 9. You need 4 bits to store those. But now you just compress it into 1 bit, actually. And like it's a lossy compression, but it's, in terms of memory, it's a huge improvement. So does it make sense? Does a scalar optimization a scalar quantization make sense to you? Okay. Okay. If there is something that is a bit vague, just ask me anytime you want. Okay. So another approach is vector quantization, which is basically the same thing as clustering. So you want to represent different clusters, different vectors in each cluster by the centroid of that cluster. Very simple approach. And at the end, you don't store all the vectors in that cluster. You only store one centroid of that cluster. And basically, you build a codebook, which is the set of centroids. And then during queries, you just need to encode your query using the centroids in a way, and find the closest centroids in the vector, in the code book, and then just traverse those specific clusters. At this point, you can also additionally query the actual vector from the disk or somewhere else from slower storage, and compare your vector to the actual value of the compare your query to the actual value of your vectors. But the nice thing about it is that you don't really need to store all of your vectors in memory. You just need to store your vectors in the disk, and whenever you want to be very, very accurate, you just query to the disk one time, or like very few number of times, and just check the exact distance at that time. So this is basically vector quantization. Again, this is a clustering, based on clustering approach. And yeah, it doesn't really have much more thing than clustering. Is it clear? Okay. So the most fun thing, actually, the most fun technique in quantization is product quantization. There is a bunch of research in product quantization, like optimized product quantization, and there are endless research. Like people publish in this area very, very oftenly. The idea in product quantization is that what if, instead of storing centroids for the whole vectors, we store centroids for the subpartitions of our vectors. Like, let's say the picture I'm representing here is corresponding to one vector. We divide that vector into 4 different segments. Like if you have a 128 dimensional vector, we are dividing it into 32-bit segment, 32 dimensional segments. And for each 32 dimensions, you create its own clustering, its own clusters. And then you only need to store the centroid or the ID of those clusters for that specific subpartition. This has a benefit of storing usually a smaller number of partitions, a smaller number of clusters for each subpartition. And because of that, the number of bits you need to allocate for each cluster identifier is smaller than the first approach. So again, you split the space into M chunks or M subspaces, cluster each subspace to some tunable number of clusters, and assign the ID to each subspace in a centroid. The ID here is very similar to the codebook in the previous method. So to see an example, let's look at the bottom right picture. To quantize a vector V, you just need to quantize each subpartition of that vector. So at first, you split the vector into its 4 subpartitions, and just find the partition that vector and the cluster that vector belongs to in each subpartition. Replace each chunk with the ID of the nearest centroid of that subpartition, and then just simply concatenate all of those IDs together and come up with a new vector, the compressed version of the vector. It's much more efficient than the first 2 methods. Scholar it's much more efficient. It's usually like they combine this method with the other methods, but this method is usually much stronger and widely used, much more stronger and widely used method. So Demetri asks, not sure how the clustering achieves compression. Okay, so the thing is that basically clustering represents each vector within the cluster by its centroid, right? So imagine in each cluster you have 10 vectors, and you're representing these 10 vectors only by one centroid. So at this point, you achieved a 10x compression ratio, right? Because you don't need to store vectors anymore. You only store the centroid of the vectors. Oh, let me also clarify this. It's not exactly the clustering approach, because in clustering approach, we are still storing the actual vectors in the memory. Right now, I'm talking only about quantization. So I'm assuming I'm only representing each vector by its own centroid. So I'm, disregarding the actual vectors and just representing them by the centroid. And because like usually each cluster has many vectors, and we are not storing those vectors, we are only storing the centroid. There is this compression ratio. The compression factor is very high. Does it make sense? Perfect. So any question about product quantization? It's a very nice, and I think generally speaking, interesting method that it's also, people use this technique in other domains, like even in in just simple compression, people use this technique. So I think it's nice to understand it very well. Okay. So I guess that's it about quantization. Just want to mention that you can combine all of these techniques together. Like you can imagine that you have an index plus index. Like you can imagine you have an IVF index plus an HNSW index. Basically, you create clusters, very small clusters, and then just create a HNSW on top of the centroids of those clusters. It's like you are finding the cluster by using HNSW, but at the end you are traversing each cluster. Each cluster is actually representing bunch of vectors, and like people use it in the industry a lot. The other thing is that people also use clustering with product quantization. So they basically, in the build phase, they partition the vector space into cells, again, into clusters during clustering. And then they learn a product quantization for each compressed vectors. So basically, they represent each centroid by its actual vector, but for each vector that belongs to the same centroid, they compress those vectors. And they compress it very efficiently because now your search space is very smaller. It only belongs to the same cluster, so you can do a bunch of scalar quantization techniques, and then you can apply PQ on top of that, which even gives you more compression factor. So yeah, so basically that's it. At the end, just give you a summary. Vector database is highly efficient for storing high dimensional vectors, and we can do efficient search on top of that. And they're optimized for similarity search. And right now it's a very hot topic because semantic search and embedding retrieval is very important in AI-based, LLM-based agents. So that was all. I hope you learned something today. So very good question. Sometimes we do that, sometimes we don't. So let me give you an example. There is this system, DiskKNN, which I think was developed in, I'm not sure, in Microsoft or Facebook, but they have a layer of product quantized vectors, which basically they do the first layer of their search on the product quantized version of all of the vectors. They store that in memory, and they do the first pass of the search very, very fast, and they come up with the good and new starting point in the actual search. So in a way, the product quantization helps you to store some information about all of your vectors and do some high-level search, and then find a new starting point, a more relevant, probably closer to the target starting point, and use that starting point to traverse your a bit slower to traverse graph, which some part of it resides in the disk or over the network, faster. Like you can start from a better position, so you can traverse it faster. So in this case, for example, you store both the product quantized version and the actual vector in your index. One index resides completely in memory. The other index resides, some part of it resides in the disk. But we have also some other databases that the index is basically only for product quantized version of the vectors. And the actual vectors, you don't store them in the index, you just store them in the storage, like contiguous to each other. So basically, if you really want to do exact search for your vectors, you need to retrieve all of those vectors from the storage, which is a costly operation. But usually in the industry, people combine those techniques. So they store the product quantization for faster and more scalable search. But when they get very close to the target, query, at that point, it matters to be more accurate. So they retrieve the actual vector and try to, spend some time finding the more exact top K nearest neighbor. I didn't also introduce another method here. There's this other method that basically stores the residuals of each product quantized vector. So you can assume at each phase, at each product quantization phase, you are losing some information. You can imagine that you are storing the residual of the loss, like the loss itself, again recursively by product quantization. So you can do that in two phases in a way. And they store the residual sometimes still in memory. So even in that case, they really don't need to go through they don't need to access the disk anymore. So there are a whole bunch of techniques that is happening, but the takeaway here is that product quantization surprisingly doesn't harm recall, even if you are not storing the actual vector, if you are not retrieving the actual vector. Product quantization only costs you 1 to 5 percentage points in accuracy, which is negligible in real world data, in real world query distributions. Does it make sense? Okay, nice. So any other question? Okay. No, I don't think so. Also, make sure to ask Akshay about it, but I'm almost sure none of these things will be on final. Okay. Thank you so much, guys. I hope you learned something. If you need anything, if you're interested in this thing and you need more, I attached my email. I also share the recording of this lecture and also share the lecture itself. And thank you. Okay. Have a good day.